All right, we've all done it. We've all gotten in an elevator, pressed the button and waited for like 30 minutes. Press the button 10 more times because you're in a hurry. And then finally the doors close and it takes off and you're going up. And you feel a little bit of you feel the floor push up on you. When you're feeling that, you're accelerating. As soon as you start to move at a constant velocity, you don't feel it anymore. Okay? But when you first take off and start to accelerate, you feel the floor push up on you and your knees bend a little bit. Okay, what we want to know is if we're in an elevator and the elevator is accelerating upwards at 2.0 meters per second squared, what's the normal force? Remember, last video we talked about weight and the normal force. And in that video we talked about a coffee cup sitting on a table going nowhere. And in that situation, the normal force up, the weight down were equal and opposite, and they canceled. And that's why the cup goes nowhere, because the net forces were zero. Okay? Now let's see in this case if the normal force is equal to the weight, as it was for the coffee cup. Let's draw a free body diagram here. Okay? For you, you're riding on the elevator. There you are, condensed to a point. What forces are acting down on you? Well, as ever, the weight. As long as you're near the surface of the earth, you got your weight, you got your mg happening. Can't avoid it. The other force acting on you is what? Or another force acting on you is what? Class? The normal force, right? The floor pushing up on you. And that's it. Those are the only forces acting on you. No X forces. They're all Y. N is positive, it's up. Weight is negative, it's down. Let's apply Newton's second law in the Y direction. Again, notice the pattern. Ding, ding, ding. Free body diagram. First thing I did. Second thing I did. Write down Newton's second law. It's a pattern. You're going to see it over and over and over again. Okay. Now this formula here doesn't have an N in it. Right? But it will. Because we're going to unpack the left-hand side and write down all the forces in the Y direction. And when we do that, we're going to get N up, right? If you look at the free body diagram, it will tell you how to write out your forces. The left-hand side of Newton's second law. Right? Look at your free body diagram. There it is. We got one force up, we got one force down. The force up we call N, the force down we call W. So N minus W. Minus because it's down in the negative Y direction. Equals M times A. And we're going to drop the subscript on the A because all the motion's in the Y direction. There is no X motion, so we don't need to distinguish between A and AY. It's just A. All the A is in the Y direction. Okay. Now in this case, A is not zero, as it was for the coffee cup, right? The coffee cup just sitting there minding some business, A was zero, right? You go to your kitchen table, put a coffee cup down there, and watch it for a while. It ain't going nowhere. Unless your cat comes and knocks it off. But if it just stays there by itself, nothing untoward happens, your coffee cup's just going to sit there. There's no acceleration. In this case, not so. In this case, you are accelerating upwards at 2.0 meters per second squared. So the right-hand side is not going to be zero. So we can solve this for N. We're looking for N, right? We want to know what the normal force is. Easy enough to do. Add W to both sides. First thing to notice here, the normal force is not equal to the weight as it was for the coffee cup. It's equal to the weight plus something. Okay? It's more than the weight. And there's a nice way to write this, actually. You can write the weight is mg. Remember, the weight is always and forever mg. In fact, I could have just called this vector mg, but so this is going to be mg plus ma. We can factor out the m. Remember factoring? You might have not seen it since 11th grade, but it's still around and it still works, factoring. So mg plus a. So now we can put our numbers in and find the normal force. Normal force is going to be 55 kilograms times 9.81 meters per second squared plus 2.0 meters per second squared. When you do your math, you get 650 newtons. Normal force is 650 newtons. Now, if you compare that to the weight, right, let's figure out what the weight is. Weight is mg, 55, 9.81 newtons. What you get there? The weight is 540 newtons. So you can see that the normal force and the weight are not equal to each other. When that elevator is moving up, accelerating upwards, it is as if you actually put on weight for the way it feels to you. You feel like, just for a moment, that you're 650 newtons heavy. When if you were just in your bathroom on your scale, you'd be 540 newtons heavy. Okay? So when it's accelerating, your weight goes up. That's why your knees buckle a little bit and you feel a little bit of a stress in your body. Okay? And by the way, your scale, just so you know, your bathroom scale, so your standard bathroom scale reads normal force, not weight. Okay. So if you were to put the bathroom scale on the elevator with you, you would see your weight go up as it accelerates. Now, it's not going to keep accelerating the whole time. It's going to reach a constant velocity. Acceleration is only that little bit at the beginning where you feel yourself a little heavier, and it's a little bit at the end when it stops and you feel like your stomach moves a little bit. Feel a little bit of the funny, goofy feeling in your stomach when it comes to a rest, and you keep moving a little bit. Your inertia keeps you moving, and your stomach feels a little bit goofy there for a second at the top. Okay. So your bathroom scale actually reads the normal force, not the weight. But if your bathroom is not accelerating, which it usually isn't, they're the same thing, like the coffee cup. Okay. Like the coffee cup. But if you were to take your bathroom scale into the elevator and read it as you're accelerating upwards, it would show more than your weight. And by the way, if the acceleration were backwards, were the other way, your scale would read less. How would all of this look different if the acceleration were negative? Okay. Let's say that our acceleration, so we're moving up but slowing down. This is where you get to the top of your trip and you start to stop. During that brief amount of time, the acceleration is down. So your normal force is 650 newtons when acceleration equals 2.0 meters per second. But what about if acceleration equals negative 2.0 meters per second squared? And you're moving upwards, but you're slowing down, so the acceleration is down It's stopping you. And your stomach feels light and a little bit funny. Well, the only thing that's going to change is this sign right here. Right there. The acceleration here, if the acceleration were negative 2 meters per second squared, that would be a negative sign there. And in that case, the normal force would come out to be smaller than your weight, 430 newtons. Okay. So all the pink here, all the pink that I've drawn is for when the acceleration is in the negative direction. Okay. So if you're moving up and accelerating upwards and A is positive as it originally was, you're going to weigh more. You're going to feel like you weigh more than your weight. If the elevator is moving up, it's slowing down, you're going to feel like you're less than your weight. You're going to feel 430 newtons. And the 430 would come out if you put a minus sign right there. Okay. All right. Next up, we're going to talk about dragging a suitcase across the airport floor. Should be fun. Oh, I'm not done. I did want to say that the normal force here and the weight do not balance out. I drew the normal force a bit longer than I drew the weight. I tried to anyway. So they don't balance out to zero. They don't cancel each other. That's why you accelerate upward, because the upward force is stronger than the downward force. So when you sum them up, they don't get zero. You get a positive force. There you go.